Hi everyone, hope you had a good break and are looking forward eagerly to the exam season. So as I promised last semester, I'll be uploading a number of revision videos. This is one of them. There'll be a couple more, actually probably 3 more uploaded along with this one, hopefully if things go to plan. I'll also be organising a number of engagement sessions so we can go over the material from last semester, and we'll be uploading exam run-through videos as well. They should be going up at the same time as this goes up, so they should be over in the list over there or down there, over there, wherever. Anyway, this particular video is about the thorny problem of quantum measurement, the measurement problem as it's called, and it teases out a number of different aspects, in particular superposition, demonstrating that superposition isn't just a quantum effect, that it's something that's, ported over from the classical world and the physics of waves. But of course there are differences, big differences between the quantum world and the classical world, particularly when it comes to measurement. And the latter half of the video talks you through the measurement problem, talks you through the simulation I wrote back a few months ago in terms of taking the particle in a box, measuring energy, measuring position, measuring momentum, what exactly is going on in that simulation, filling in some of the background beyond what's in the blog post, and I hope it'll be helpful. Okay, let's make some noise. So we've got a really simple demo just to remind you of standing waves on a string. It's about as Heath Robinson as it gets. It's held together with gaffer tape and blue tack and various bits and pieces I found lying around the office. Just an old loudspeaker which I'm driving with a signal generator which is connected to, you can't see it but hidden behind this screen is a power amplifier which is going to drive this loudspeaker, and we're going to be able to tune the frequency and pick up on different resonances of this string. Which, as you can see, has got a certain tension, it's got weights hanging from it. You've done a similar experiment back in first year in terms of the sonometer, some of you will have. It's just the same idea, we're picking up different standing wave resonances of this string. So, let's turn things up, it might get a bit noisy. Okay, so let's tune things in. Okay, now I think you can see it pretty well. Got node here, antinode, antinode. That's our lowest resonance, that's our fundamental resonance. We call it the first harmonic. Engineers and physicists differ a little bit in this, but we're going to call it the first harmonic, it makes life easier. So it's at about 23 Hertz, so we should expect the next resonance around about double that value, so let's tune into that. See if we can find it. Okay, there's our second harmonic with our node in the middle. Antinode, antinode, node in the middle. Hope you can see all this. So we go to the next highest, which is going to be around about 70 Hertz off that order. Node, node, antinode, 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 third harmonic. And let's go to the fourth. Let's see if we can get the fourth. Okay, there we go. Node, 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 antinode, 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 fourth harmonic. We could continue to go high up, but that makes an awful racket. So let's move on and go to something a little bit more musical. Okay, so that particular example of a vibrating string didn't make particularly melodious sounds. However, obviously the same principles hold for any musical instrument, any string musical instrument. We'll take this one, we could choose a guitar, we could choose a violin, we could even choose a piano, just hitting strings with a hammer in that case. But it's the same idea. When I pluck a string, what I'm doing is I'm exciting those resonances we saw, n equal to 1, n equal to 2, n equal to 3, n equal to 4, but I'm not just exciting one, because if I just excited one, that's a pure sine wave, and it would be the most boring sound ever. If all we did was excite just one resonance, then everything would sound like a whistle. Every single musical instrument would sound like a whistle. What gives the musical instrument its character and its sound, and what gives anything really its timbre and its sound, my voice, your voice, anything we listen to, is the combination of the different frequencies. And in this particular case, it's a combination of those standing wave resonances. So we can look at those harmonics, and we can look at how they're excited by doing Fourier analysis. And I spent an awful lot of time in the quantum world right at the start focusing on Fourier analysis, because it's essentially of that Fourier basis to understand the key concept in quantum mechanics, superposition. Now, superposition is usually dressed up as this weird quantum effect, but it's not. Superposition underpins what we're about to hear from this. It underpins everything in the world around us in terms of we take waves, we sum them up in the right way, and we can generate whatever pattern, whatever sound we like, just by building up that waveform from a summation, a superposition of sine waves. Or more generally, in terms of a superposition of basis functions or basis states in terms of quantum mechanics. So let's take a note, let's take a sound on this instrument and break it down into those component harmonics, into those component frequencies, into those component standing wave resonances, into those component basis functions or Fourier components. We spent a lot of time at the start of the module looking at Fourier analysis for exactly this reason. So on the screen right now, we've got a spectrograph, and on the x-axis is time. You can see it's picking up my voice as I speak, and it's breaking down the waveform for my voice into its component frequencies. Along the y-axis, we have frequency and the intensity. The brighter or the colour, the more yellow the colour, the more of that frequency there is. The darker the colour, the less of that frequency there is. Okay, so let's break the bass down. That's a fairly complicated mix of frequencies. Let's instead just pick out one single note. Let's pick out an E. Now, what you can see when I shut up talking, I'll play the note again, are sharp lines going across the screen in time. Those represent the harmonics. Those represent the Fourier components, the standing wave resonance, that n equal to 1, n equal to 2, and n equal to 3, that make up this particular note. All of them sounding together. What we have is a waveform, and this is showing us the superposition of the functions that we need to create this waveform. So I play the same note in two different ways. I'm just going to play it with my thumb here. So you can hear we get quite a bassy sound. It's quite low end, the lower frequencies are contributing. Let's instead now play it here, and I'm going to do it with a pick. So it's the same note, just played in two different ways. Okay, before I move to the blackboard to put some mathematical bones on these concepts, and also to see the parallels with the quantum world, and particularly with quantum measurement, just a very, very brief demo of the uncertainty principle, given that I've got the microphone and the spectrum analyzer set up. So I've banged on a tedious and interminable length during the module about the fact that the uncertainty principle is basically just an example of Fourier transformation in action. Something that's limited in time has a broad frequency spectrum. Something that's limited in space has a broad spatial frequency spectrum. We can do a really simple demo of that. So here's a signal that is not particularly limited in time. And you can see that one pure tone, very narrow frequency spectrum. So wide in time, narrow in frequency. Let's take a time limited signal. And you can see that you've got a very broad band of frequencies. Narrow in time, broad in frequency, broad in time, narrow in frequency. That holds for time and frequency, but it just as well holds, as we've seen multiple times, it holds for space and reciprocal space, or space and spatial frequency. Okay, over to the blackboard. Let's put some maths on top of this, and then let's introduce and put this all in the context of the quantum world. So as you saw last year from Newton and Einstein, there are obvious parallels between those waves on a string and a particle, which is wave-like characteristics, a quantum particle confined in a box in a potential well. In that we've got the same idea. We've got, let's draw a particle in a box that we've seen before almost an infinite number of times now. Here and here a wave function must go to 0 because the potential out here is infinite. And we set it up deliberately that way, that infinite potential, to ensure that there's no possibility out here for the particle to exist. Here's our n equal to 1, n equal to 2, n equal to 3, etc., etc., etc. So obvious parallels between that and what we've just seen. There are striking differences as well, however. Fill this in terms of superposition. Right, so what we have here are our sine functions, or standing waves, and we're going to write those as with the wonders of Camtasia, we'll put that over here and we'll write our wave functions as, you've seen this before so many times, where L is the width of the well. Those are our eigenfunctions for the particle in a box, the particle in the infinite potential well. In terms of superposition, you've seen in terms of the Fourier analysis how we make the base note by adding up the different standing waves. It's exactly the same idea. I cannot stress that enough. So, we'll call this psi, so it's for the quantum mechanical particle. This, however, could also represent that waveform on the bass string. This is not a pure quantum idea. This is a classical idea that applies to quantum, because quantum is ultimately about the physics of waves. So, a wave function in terms of x can be written, and actually I'm going to put the time dependence in as well. T is equal to 0 is equal to sum over n of these functions, where the Cn is a coefficient that tells us how much each of these basis functions we need to represent our waveform. So one reason I played that note on the bass in two different ways is, let me go get the bass. You've seen many times, you've set up many problems in terms of this is the initial state of the quantum system. Okay, let's transfer that to the classical system. Let's say this is the initial state of my classical system. Okay, so I'm about to pluck the string and I'm about to let it go. But the initial state is this. And at t equal to 0, I'm going to let go and do that. But we have a waveform. This is effectively our overall wave function describing the shape of this string. So we can represent that wave function, or we can just sketch it. And although we're talking about a classical state here, I'm just going to use the psi so you can see the close parallels. So that's what our original function looks like. We've bent the string away from its equilibrium position, and this is where I was pulling it back. I'm going to let it go. But this is the state of our system at t equal to 0. And this waveform can be made up, can be comprised, can be constructed from superposition of our basis functions. And this tells us how much of each one of those basis functions we need. So for C1, for our first harmonic, this will tell us how much we need. C2 will tell us, etc., etc. Okay, so those parallels are really important between the classical case and the quantum case. However, there's one key difference, and it is absolutely essential that you grasp this. Let me move this background. So here's our back-in-the-box simulation that I've spent a lot of time discussing. For those of you who were at the synchronous sessions, you'll remember this. We spent an awful lot of time on this. Remember that what we can observe in quantum mechanics is not the wave function itself. It's not psi x, but it's this. In terms of probability density, you need to multiply that by a volume element or a spatial element to get a probability. But this is our probability density. So, although the demonstration I showed you right at the start with that string making all that racket, well, not quite the string making the racket, but the loudspeaker and everything else resonating around it and making all that racket, the string's moving back and forth. That's not what we see quantum mechanically. quantum mechanically, these states, these eigenstates of the Hamiltonian, are stationary. So there's certainly something oscillating. The real and the imaginary components are oscillating back and forth, but remember, we're taking the modulus squared. Therefore, we get rid of all that phase information. Let's say we've got a really simple situation as we have here, just one eigenstate. So our wave function is this in terms of time. It's whatever, and we're in the first eigenstate, it's whatever our spatial state is, times this phase factor. And that's going to be 1. Remember this, what's E1 over here? So this has got units joules, this has got units joules second. So this is a frequency. So this is an I over omega t. So what's sweeping back and forth, there's certainly something oscillating, but it's something we cannot observe. It's sweeping back and forth, real, imaginary, real, imaginary. That's where the oscillation is. But what we observe is this, which will be, what's this? E to the minus I E1 t over h bar. What's the complex conjugate of that? Well, we just make that positive. E to the minus something by e to the plus, exactly the same thing, gives us a 1. So we lose all information on the phase. We can't see this oscillation from real to imaginary. All we can see is the modulus squared. The other way of thinking about that, in terms of complex numbers, going right the way back to what you did in first year. So we've got our real line, we've got our imaginary line, we've got our vector. This is our phase angle. This is rotating round. If I can do something that... Okay, I know it looks a bit like a potato, but then all my circles look a bit like a potato. That's, for me, that's not too bad. What we can't measure is this angle. What we can measure is this length. It's key. So there's a big difference. Although we've got these parallels between the classical and the quantum case in terms of superposition, the big difference is that in one case we can see that oscillation of the string for a given eigenstate, or given Fourier component for a given resonance. In quantum mechanics, if we've just got a pure resonance, if we've got a pure single component, a single eigenstate, we don't see it oscillate. However, let's add in another eigenstate. In this case, we'll add the second one in. And let's run it. What do we see? Now we see oscillation. So, with this simulation, now we have two different eigenstates, but what's absolutely critical is that those two eigenstates have different rates of oscillation between real and imaginary. So in one case, we've got e to the minus I E1 t over h bar, and for the other one, we've got e to the minus I E2 t over h bar. E2 is actually 4 times E1 if we're talking about the infinite potential well, because our energy levels goes n squared. And so what you have then is now we have a temporal dependence, because what you get the product of these two things, you're going to have a term which depends on the difference between E2 and E1. And that gives us our temporal dependence. And another key difference in terms of the classical and the quantum world, although the superposition, there were many, many parallels. Here's another key difference. So we're going to write our wave function, t equal to 0, in terms of this superposition. Well, these are the basis states of our Hamiltonian. The probability of measuring the nth eigenvalue associated with the nth eigenstate is given by that. And we're going to, in one of the exam run-throughs, you've already seen this a number of times in the coursework, you've already seen it a number of times in the worksheets. We're going to do 2, I think, worked exam run-throughs, 2 problems, which really focus in on this Born rule interpretation in terms of how the probabilities are related to the superposition. and the original starting state of the system. So if the original starting state of the system only can be written as the sum of just 3 eigenstates or just 2 eigenstates as we just had, then you've only got a probability for measuring E1 or E2. There's no third eigenstate in there, there's no fourth eigenstate, it hasn't contributed to the mix, so there's 0 probability of measuring it. These ideas are of course not at all simple, and a number of you asked me and emailed me and said, would it be possible to set up a simulation of the measurement process, which is what I did, and this is what's here. And so we can start off, our system starts off in a state, let's write it in bracket notation, which looks like this. This is our starting state. So we've got the first eigenstate, the second eigenstate, and the third eigenstate of the Hamiltonian. We've got twice as much as the first harmonic as we have of the other two. So we can set that up in terms of our simulation. This is what that looks like. So you see it's oscillating because we've got a mixture of eigenstates in there. It's not in a pure eigenstate. Let's make a measurement of energy. Notice what happens. We collapse, to use the wording of the traditional Copenhagen interpretation, we collapse the quantum state into an eigenstate of the operator associated with the measurement. In this case, that operator is the Hamiltonian operator. We've collapsed it into that state, and there it stays forevermore if we measure energy. If we measure energy again, we get exactly the same value with 100% probability. Measure energy again, exactly the same value with 100% probability. Notice that the time is being reset. This simulation is for the particle in a box. There's a lengthy blog post. Read the blog post. It's at a level, I've written it at a level that is commensurate with what we've done in the quantum world. So there's a list of suggested tasks associated with this quantum measurement simulation. Go through those. Make sure you understand what's going on. That's what happens with energy. But of course we want to measure things other than energy. We want to measure position or momentum, for example, as well. And if we make a measurement of position, the simulation is set up so that our wave function becomes something that looks like that. So it's a Gaussian wave packet we've covered elsewhere. And it's associated with certain measurement. Now, we've talked about delta functions a great deal throughout this module. A delta function is a really unrealistic and physically impossible example of a measurement process. It's very helpful in terms of getting to the bottom of quantum theory and understanding key elements of quantum theory, but it's not a good representation of what actually happens in a measurement. No measurement is absolutely perfect. You know this. You've been in, the majority of you have been in undergraduate labs. Which there's a reason we spend so much time on uncertainties and error analysis. So there's some spread of values that are possible. So when we make a measurement, what we do is our wave function becomes this. We've got some value, mean value, and the resolution of that measurement, we don't have perfect resolution, is modeled or represented by the width of this wave function. But this, just like we had for the bass string, where we had this, again, we can represent this in terms of a superposition of the basis states, the eigenfunctions of the Hamiltonian. So let's do that. Before we do that, let's slow the simulation down dramatically. Like this. Now I'm going to make a measurement of position. Hit the position button. So, I've slowed it down completely, so time is stopped at the moment. So there's our Gaussian wave packet representing our measurement of position. I'm going to let's time flow forward now. And what you can see is it's spreading. The reason it's spreading is because that wave packet comprises all those different states of the Hamiltonian. So in terms of time, we have this. And now we also have our temporal component, our phase factor. And it's this which has given rise to that spreading. We've spent a lot of time in terms of Gaussian wave packets. Go and look at chapter 3 and the associated videos. And that's what's giving rise to this spreading. And when it hits the wall, when it spreads out and hits the wall of the infinite potential well, the infinite potential container, these are waves, so they get reflected, they get bounced back. And if we speed this up, you'll see that very, very quickly we end up with a wave-like mess. Because what we have is all the various eigenstates that contribute to our initial wave function. They're moving in space, and remember that they disperse because their velocity depends on their energy, and because we've got a range of different energies, we have a range of different velocities, so they all disperse at different rates. And our initial wave packet falls apart. We now measure position again because our wave function is dispersed across the entire region of the box. Then we get a different measurement. The probability is we're going to get a different measurement with very high probability of position. Now, however, if you measure energy again, because we've got a much broader range of eigenstates contributing to our overall wave function, now we've got a probability of not just measuring the first, second, or third eigenstate, we've got a probability of measuring n, the nth eigenstate. And that's what happens. So if I make a measurement of energy now, we collapse it into an eigenstate, the Hamiltonian operator, but because our wave function we started with has many, many more eigenstates contribution to it, then we've got a probability given by this modulus squared of this of measuring one of those higher order eigenstates. Okay, that was a recap. I hope that's helped, and I hope that's given you some insights. As I say, I can't stress enough, go through that list of tasks. You'll get a great deal of insight into just how quantum mechanics works by playing with this simulation. We'll spend, we're going to do a number of engagement sessions in the run-up to the exams. Very happy to talk about that, or obviously any other aspect of the first semester of the course. Email me, a number of you have been emailing me throughout. Also, if you see any typos in the notes, please let me know and I'll fix them as soon as possible. And in the next video, the next videos, gonna do exam run-throughs. See you soon.